So what is a Cherenkov telescope? This is, from 1952. Really, it started off as what, we sort of fondly referred to as a light bucket. It really was not very advanced. You need a mirror to catch the, ultraviolet photons. You need some sort of detector that detects the photons, and you need something that triggers off of the air shower events as they're occurring, and you need some way of reading out the data. And so this is just this, very simplistic device here, where I, want to be careful to say that this is really just, as the name implies, counting light. It's not imaging it at all. This is just saying, do I have a photon or not? And so then you have to start worrying about, well, are there other things that create these air showers? Well, of course, in fact, there, 1,000 times, depending on the energy range you're in, 1,000 times more cosmic rays per gamma ray. And so you have to really get into understanding shower physics at that point to think about how to distinguish the cosmic ray background from the gamma ray signal. And there, actually, as it turns out, a number of ways that you can do that. They're isotropic. In other words, the cosmic rays are charged particles, so they interact with magnetic field lines. So you expect them to come in isotropically throughout the atmosphere, whereas gamma rays are neutral. They don't interact with magnetic field lines. They come straight, assuming a variety of things, from the source. Trying to put together all the properties that allow you to distinguish between the cosmic rays and the gamma rays, one comes up with the idea of an imaging detector. Because what you really are trying to do is take the fact that you have that clumpiness in the cosmic ray showers, and you have the pointing to the source of the gamma rays, and saying, well, if I could actually not have a light bucket that just counts the number of photons that come in, but actually look at the distribution of the cosmic ray air shower, the air shower, whether it's cosmic ray or gamma ray initiated, on the camera, and figure out some way of parameterizing that image of the shower. Is there some way that I can use that to my advantage? And of course, I would be standing here if the answer was yes, we can. And so, thus the birth in 1968 of the Whipple 10 meter, which is out in near Tucson, Arizona as well. It's sort of the grandfather of all the imaging Cherenkov technique. And it basically added an imaging camera to that very simple Jolly-Galbraith light bucket. Telescope, and again, this is one telescope, the Whipple telescope. You have your Cherenkov light pool that comes down and hits it. It creates the image of the shower and this is an idealized camera here, nice even pixels. And the way that it images the pointing back to the source is pointing down into the middle of the camera, so that if this is one way you can start distinguishing between the cosmic rays and the gamma rays. The cosmic rays, remember, are isotropic, so they should be spread. Their reconstructed directions will be all over the place, randomly distributed. More is better. So we go into stereoscopy, or telescope arrays. So you've got your Cherenkov pool, which we've done before. Now you have more. And so you get a better reconstruction of the arrival direction, or the impact parameter is what we call it. Of course, you're then able to reject the muons, because the muons are falling next to one of the telescopes, and if they don't show up in more than one, then you can reject that event.
So a typical muon ring will not intersect several.
No, not at all. The baselines are long enough that's correct. Okay, so this is a great idea. So there's 4 operating on a kangaroo down in Australia. He's having some problems, so they're at the moment. But MAGIC is actually a monolithic dish. It's 17 meters. TESS in Namibia and VERITAS are very, very similar. They're both 4 telescope arrays. Okay, so hopefully most of you know that active galactic nuclei comprise a large number of types of sources. It's sort of a veritable zoo of astronomical objects. Most of them are radio quiet, sort of 15% are radio loud, and in particular the radio loud, the VLAC objects are TeV emitters, and those are the ones obviously that we're very interested in. We call them blazars. They are characterized by a double humped spectral energy distribution, where, and this, I actually kind of like this slide because it shows the images of Markarian 421 across the set of wavelengths. So the spectral energy distribution is characterized by this double hump, the gamma rays being up here, and the basic idea behind this is that in these jets, there's very large jets that are driven by the accretion power in the AGN,